So, you know that feeling when you open your car door in the middle of July and just that wave of stagnant, trapped heat hits you right in the face?
Oh, yeah. It feels like walking into an oven.
Right. And your very first instinct is just to crank the air conditioning to the absolute maximum just to survive the commute.
It's a very visceral, I mean, human survival mode.
Yeah,
We are biologically wired to just get the temperature down as fast as possible.
exactly. But while you're sitting there worrying about your own comfort, the car itself, specifically if it's an electric vehicle, is fighting this much more complex, high stakes battle for its own survival right beneath your seat.
A battle that completely defines how the car operates, yeah.
Yeah. Welcome to the deep dive. It is Thursday, June 25, 2026, and this one is custom tailored for you, our listener, the learner.
We've got a really great stack of sources today.
We do, yeah. A bunch of technical excerpts and engineering guides, all focused on EV thermal management. Today, we are decoding the hidden engineering that determines why some electric cars can handle, extreme summer road trips, while others just fail prematurely.
And leave you completely stranded, which nobody wants.
Right. Our mission today is to help you learn something entirely new about the machines sitting in our driveways and to arm you with a practical, no-nonsense checklist for evaluating EV tech yourself. So, okay, let's unpack this. We have to start with the core problem, the heart of the car.
The lithium-ion battery.
The battery, yeah.
It's an incredible piece of technology, but it is fundamentally fragile when it comes to its environment. These cells have a very specific, narrow operating window. Engineers literally call it the sweet spot.
And what is that sweet spot exactly?
It sits strictly between 20 degrees and 45 degrees Celsius.
Okay, so for those of us doing the conversions in our heads, that's roughly what? 68 degrees to 113 degrees Fahrenheit.
Exactly. It's basically room temperature up to a very hot summer day.
So what happens if it gets hotter than that?
Well, if the battery cells drop below or climb above that specific window, the chemistry starts to turn against you. Specifically, when they get too hot, you trigger accelerated degradation.
Like permanent damage.
Yeah, the internal components of the cell physically break down. You get a permanent loss of battery capacity, which means you permanently lose driving range.
Oh, wow.
And to stop that from happening, the vehicle's computer will just aggressively step in and throttle your performance.
Which means the difference between a car that lasts 200,000 miles and one that dies early almost always comes down to how it manipulates heat, right?
Absolutely. That underlying necessity is what created what we call the Great Divide in automotive engineering. Manufacturers had to figure out how to get rid of heat, and they split into two completely different architectural approaches.
Right, air cooling and liquid cooling. Let's look at air cooling first because it's the older, simpler method.
Very simple. It's totally passive.
Yeah, it relies on ambient airflow from the car driving down the road or just internal fans blowing air over the battery pack.
But there is a fatal flaw in that design. The thermodynamic efficiency of air cooling drops off an absolute cliff the moment the outside ambient temperature goes above 35 degrees Celsius.
I kept thinking about a cup of scorching hot coffee when I was reading this. Trying to air cool an EV battery is basically like trying to cool down a boiling cup of coffee just by blowing on it.
That's a great way to put it.
Like, it might work eventually if you're sitting in a cool room, but if the room itself is 100 degrees, blowing 100-degree air onto the coffee isn't doing anything.
And the problem goes even deeper than that, because unlike a cup of coffee, an EV battery is actively generating its own internal heat while you drive or charge.
Oh, right. So you're trying to cool the outside with hot air while the inside is still cooking.
Exactly, which is why liquid cooling is the active standard now.
So, staying with the analogy, liquid cooling is like taking that hot coffee cup and submerging it completely into an active circulating ice bath.
Instantly effective.
It works forcefully. It uses a dedicated coolant running through plates directly alongside the cells, aggressively pulling heat away regardless of the weather. But I really pushed back on this when reading the sources.
Oh, how so?
If liquid cooling is so clearly superior and air cooling fails at 35 degrees, why would anyone ever build an air-cooled EV? Especially because it triggers this terrifying thing called rapid gate?
Yeah. What's fascinating here is the historical context. But you're right, Rapidgate is the ultimate nightmare for a summer road trip.
Tell me if I have the scenario right. You're driving an air-cooled EV on the highway during a heat wave. The battery gets incredibly hot. You pull up to a fast charger, hoping for a 20-minute top-up.
Right.
You plug it in. But because there's no liquid to carry away the heat of the charge, the car's software panics. To prevent the cells from melting, it triggers protection mode.
It drastically restricts the power.
Yeah, so instead of a 20-minute pit stop, you're stuck sitting there for hours because the car refuses to accept power fast enough just to save its own life.
That is exactly the mechanism of Rapid Gate. The software becomes a bottleneck to save the hardware. But the reason manufacturers built these cars initially was purely economic.
Because it was cheap.
In the early days, primarily with entry-level models or budget city cars, air cooling was incredibly cheap to manufacture. No pumps, no fluid reservoirs, no complex seals to leak.
I mean, I guess if you were just driving a few miles around a mild weather city and plugging into a slow charger in your garage overnight, it was fine.
It was completely adequate for that low-stress use case. But as consumer expectations shifted, people wanted ultra-fast 150 kilowatt highway charging.
Right, and that architecture became a massive liability, which means liquid cooling is now the non-negotiable standard for longevity. You absolutely need it to guarantee predictable fast charging.
But dropping a battery into an ice bath creates a massive new problem.
The energy cost of the ice bath itself.
Exactly. Running a heavy-duty AC compressor just to chill the fluid requires a ton of electricity.
So you save the battery from melting, but you drain the very energy you need to drive the car. You kill your range. How do they resolve that?
Well, the solution is integrated thermal systems. Manufacturers had to manage massive thermal loads without bankrupting the battery. And the foundation of this is the heat pump.
Okay, wait, a heat pump? I thought that was just a winter efficiency tool to keep the cabin warm.
That is the most common misconception, honestly.
Yeah.
We deeply associate them with winter. But a heat pump is not just a heater. It is a bidirectional energy mover.
Let's break that down, because I think a lot of people get confused by this.
Think about traditional electric heaters, what the engineering guides call electric resistors. They just burn electricity to create heat, like a toaster.
Right, highly inefficient.
Horribly inefficient. A heat pump doesn't create heat from scratch. It physically moves existing thermal energy from one place to another. It's like a refrigerator running backward.
Okay.
It can scavenge heat from the outside air and move it into the cabin in the winter. But crucially, it can also run in reverse to pull heat out of the battery in the summer.
And this movement is the core of what modern engineers call smart loops, right? Like the integrated thermal management modules.
Yes, the ITMM from suppliers like Morelli.
It's wild. Instead of separate cooling for the battery, the motor, and the cabin, the vehicle treats the entire car as a single interconnected thermal ecosystem.
Right. These smart loops perform three vital functions. The first is heat sharing.
Which is basically thermal scavenging. Like your battery is too cold to fast charge, but your motors are hot from driving.
Exactly.
So instead of turning on a battery heater, the smart loop literally scavenges the waste heat radiating off the motors and redirects it to warm up the cold battery.
It recycles the car's own trash heat as fuel. It's brilliant. The second function is heat expulsion. When you hit extreme summer conditions, the system intelligently funnels all that excess, dangerous thermal energy straight to the primary radiators to dump it out of the car.
And the third function is selective active cooling. Using electronic valves, it cools only the specific components that need it. If the inverter is overheating but the battery is fine, it routes coolant just to the inverter.
Saving massive amounts of energy because the pumps aren't running at full blast everywhere.
And we are seeing incredible implementations of this. VW has the MEB platform linking battery and motor cooling. But here's where it gets really interesting. Tesla's Octovalve.
The Octovalve is a marvel.
When I first read about it, I pictured a frantic traffic cop in an 8-way intersection, instantly routing hot and cold traffic precisely where it needs to go. But I'm struggling to picture how it doesn't turn into a plumbing nightmare.
How do you mean?
If you have hot fluid from the motor and freezing fluid from the AC hitting the exact same central valve, how does it not just mix into useless, lukewarm water?
You'd think it would, yeah. But the brilliance of the Octovalve is internal isolation. The fluids never actually touch. The valve acts as a complex central manifold with multi-level internal chambers. It routes hot fluid down one channel and cold fluid down a separate channel right next to it.
Oh, wow.
The system can instantly rotate internal baffles to swap which those fluids are running on, directing energy perfectly without ever physically contaminating the streams.
If we connect this to the bigger picture, oh wait, I'm stealing your line.
No, go for it. If we connect this to the bigger picture, the vehicle is a single thermal ecosystem.
Exactly. But mechanically moving heat around is really only half the battle. The most elegant solution is just generating less heat in the first place.
Because a lot of the heat isn't from the sun, it's generated internally, especially during an ultra-fast highway charge. To solve this, engineers shifted from plumbing to electrical architecture. The jump from 400-volt to 800-volt systems.
Like in the Hyundai Ioniq 5, the Kia EV6, the Porsche Taycan. But to understand why voltage changes temperature, we have to talk about Joule's law. P equals I squared R.
Right. In Joule's law, P is power loss, which in this circuit is pure heat. I is the current, and R is the resistance of the cables. The most punishing part is the I squared.
Heat generation doesn't scale linearly with current.
No, it scales with the square of the current.
So if you double the current, you don't double the heat, you quadruple it, triple it, you get 9 times the heat. It's an exponential nightmare.
It becomes unmanageable. If you try to push 250 kilowatts into a 400-volt car by cranking up the current, the cables could literally melt their own insulation. So to deliver that power safely, you have to lower the current. You do that by doubling the voltage.
Right, so moving to an 800-volt platform, the car accepts the same 250 kilowatts, but it only needs half the current.
Exactly.
I picture a garden hose filling a bucket. You need to fill it fast. You can use a wide hose with a massive flow of slow-moving water, high current. When it hits the bucket, it creates a giant, messy, hot splash.
I like that analogy.
Or you use a narrower hose, but crank up the water pressure to the absolute max. That's the 800 volts. You get the same amount of water in, but without the messy splash. Incredible charging speed without the catastrophic heat.
And because you've reduced the heat at the source, the thermal management system doesn't have to work as hard. But to orchestrate all this, you need a conductor. Software. Specifically, battery preconditioning.
This detail genuinely blew my mind. The car's GPS navigation actually talks directly to the thermal cooling system.
Thermal management is a predictive science now. Imagine you tap a fast charger into your GPS. The car calculates your arrival time and anticipates the massive thermal surge it's going to experience when you plug in.
Because it knows that fast charge is going to hit the chemistry like a thermal hammer.
Precisely. So 20 minutes before you arrive, the software aggressively chills the battery down, dropping the temperature well below normal to create a deep thermal buffer.
So when you plug in, it's already primed. It absorbs power at max speed while the temp climbs safely back up without ever hitting that 45-degree danger zone.
It uses predictive software as a physical shield, preparing miles in advance.
So what does this all mean for you, the learner? Let's bridge this back to everyday consumer reality. We put together a learner's checklist for evaluating a vehicle's heat resistance.
The first item is critical: liquid cooling. Non-negotiable. Ensure the spec sheet explicitly mentions active liquid thermal management.
Check. Item 2, a heat pump. Don't let a salesperson say it's just for winter. It saves your summer range too.
Item 3 is the 800-volt architecture. If you do frequent road trips and fast charging, prioritize this platform.
And item 4, preconditioning software. Now, looking at this checklist, you'd think a tiny city car would melt on the highway compared to a massive luxury SUV, right?
This raises an important question, yes, because there's a very persistent myth about that. It's logical, based on how combustion engines used to work with huge radiators, but the data debunks the city car myth.
I assumed a tiny vehicle would overheat. But heat resistance is a product of architecture, not size.
Look at modern city cars from 2020 to 2023. Like the Fiat 500e or Mini Cooper SE. They are tiny, but engineered with full liquid cooling. They hold their own thermally against much bigger luxury sedans.
The problem isn't small cars. It's older architectures that relied on passive air cooling. Ignore brand prestige, ignore the size, look at the spec sheet. If it has liquid cooling, it's robust.
But if you are driving an older air-cooled car, there are firm rules of thumb.
The 34-degree rule. The guides advise that if the ambient temp exceeds 34 degrees Celsius, about 93 Fahrenheit, avoid long, stressful highway journeys. The cooling just can't keep up.
And for charging, try to travel at night. Park in the shade. But the golden rule: if you have to charge under direct summer sun, do not let that session exceed 1 hour.
Just get enough juice to reach a shaded charger and unplug before the heat overwhelms the battery.
It's about minimizing the compounding thermal load. Internal heat plus radiant heat from the sun and asphalt is just too much.
This has been such an illuminating journey. We set out to help you learn exactly how these machines fight heat and to give you a real checklist. We covered rapid gate, the octovalve, 800-volt physics, and predictive software.
It's a testament to how fast the engineering is evolving.
Yeah.
They turned basic plumbing into a digital art form.
I want to sincerely thank you, the learner, for bringing these sources to the table and joining us. But as we wrap up, there's one lingering detail that completely changes the context of everything we've discussed.
The absolute 45-degree limit.
Exactly. We spent this whole time talking about keeping the battery inside its sweet spot,
Yeah.
but the absolute maximum temperature for these advanced liquid-cooled batteries tops out at 45 degrees Celsius, 113 degrees Fahrenheit.
And we are seeing ambient summer temperatures worldwide creeping closer to that maximum line every single year.
Right. So here's a final provocative thought to mull over. If global temperatures continue to rise and extreme summer days regularly push ambient air past that 45-degree threshold, what happens?
It's a huge issue.
Does all this brilliant plumbing, the octovalves, the heat pumps, eventually just hit a thermodynamic wall? How can an AC system expel heat into air that is already hotter than the heat it's trying to get rid of? Will the EVs of the near future require entirely new battery chemistry rather than just smarter plumbing?
That is the multi-billion-dollar question that will define the next decade of automotive engineering.
It really is. So the next time you open your car door in the middle of July and that brutal wave of heat hits you like a wall, just remember the real battle isn't happening in the cabin. It's happening right beneath your feet. Until next time.